Hello. Can you hear me?
Yes, I can. How are you?
Pretty good, pretty good. How about you?
Yeah, doing all right.
Awesome. Okay, let me share my screen. So I worked through the problems on my own time, so then I could not have to go through all the uhs and ums what to do with the problems. But for the review, there's like 3 problems that Russell gave me. And so the first problem is dealing with calculating the open circuit and short circuit natural frequencies between terminal A and terminal B. And it wants you to figure out, is it are the open circuit or short circuit natural frequencies bounded or unbounded? Second problem is wanting to deal with, it's about the same steps. It wants you to create this transfer function using either MAME or name, and then calculate what is our scale constant k, and then what are the poles and zeros of the transfer function that you found. And then lastly, there is a calculate the frequency of oscillation and the transconductance GM. And this is generally, it's the same process of figuring out, do I do MAME or name, but then since there's no terminal A or B, it's just like taking the determinant of whatever final matrix you have, and then separating into the imaginary part of that determinant and then the real part of that determinant, and saying both equal to 0. And then you'll solve for omega, or you'll solve for F oscillation in one of the equations, and then you'll use that F oscillation value to solve for your transconductance GM. So I got problem 1 pulled up. Do you have any questions before I start it up, or?
Just one. I'm pretty good on, or at least I have an idea about most of those problems, but I don't think he's gone over the frequency of oscillations yet. Do you know if
Really,
that
he is
was?
not?
Because I mean, I know vaguely because I've just seen a few problems about it, like
Okay.
how to do it, but I don't think he's gone over that in class, and I wasn't sure if you knew if that was going to actually be on the.
Yeah, I can kind of talk about oscillation.
Okay.
So oscillation is pretty much you'll learn more about this in like your control system class. But generally you have your Laplace domain of this graph where you have your imaginary axis and you have your real axis, and it's all these values are, think of it as s equals 5. Let's say you actually have a transfer. Let me talk about transfer functions. So transfer function is like, let's say TF equals s squared plus 3s plus 2. And then you have, let's do s squared plus 4. I don't know, let me do 7s plus 1 or whatever. This is kind of your transfer function. A transfer function kind of tells you how is your system going to respond over time, and then how is it going to be a bounded response, or is it going to be an unbounded response? Like, if I let this system go on forever, is it going to just like freak out on me, or is it going to try to self-correct itself? And oscillation is pretty much, or you can think of in your numerator you have your zeros, and then in your denominator you have your poles. And so uh, both your poles and zeros affect this graph. But generally, if there are any poles in the right half, or like the imaginary side is, or if you have any poles where the real part is positive, like s equals 5, which would be like right here, or s equals 8, which would just be like over here or something, then that means that your time response is going to shoot up to infinity. Like if this is voltage, but if it's in this area over here where s equals -3 or -2 or -7, then it's going to come out to a final value. Now, oscillation is whenever you have imaginary values. Whenever these imaginary values come up, your final response curve can end up being, can kind of have like a little oscillation to it. It could end up looking like this. It could end up looking like this. It could end up looking like, if it's bounded, then maybe it looks something like this until it comes out to a final value, kind of like that, where it's a big oscillation and then like comes down to a little bit. So whenever we are looking for F oscillation, what we are saying is that we want the, let's say you have a transfer function. Let's say you have a transfer function where you got your numerator and you have your denominator and you have some scaling gain called K. What you're doing is you're saying that you're taking this value right here, that let's say that's s cubed plus 7s squared plus 3s plus 1 or whatever, some value of s's. This is eventually going to FOIL down into a real version of this. And or some of these parts are going to be real, and then some parts of them are going to be imaginary. And you're essentially saying the imaginary parts, set those equal to 0, meaning what value of since s equals j omega, you're going to substitute in j omega for each of these pieces. And then the j's are either going to cancel out because like j squared equals -1, so now it's a real component, or j cubed is going to equal -j, so now this would be an imaginary component since there's a j left. But essentially you're saying for all the imaginary components, you're saying them equal to 0, where you're saying this area right here, where you're going to get an oscillation kind of like this. You're trying to find the frequency where your oscillation, or where your on your s-plane, it's going to be on this imaginary axis. And that's why we set the imaginary values of the determinant equal to 0, so that we can find what frequency that works for here. Does that kind of make more sense?
Okay. Yeah, it does. Thank you.
Okay. No problem. Let me reload this. Oh. File. I guess I'll switch questions and don't save, and then reload into that question. Cool. Okay. So for this question, always for every single one of these questions, the first thing that you gotta think is, do I do name or name? Of course. If you look at this, for this kind of problem, whenever you see terminals A and B, you generally want to either attach a current source or a voltage source, depending on, is this going to be name or name. So if this is going to be name, then I want to do current sources, because name is going to be some matrix of conductances times your voltage matrix equals all your active sources, which would be the currents. And so since we would be doing, it looks like name, because you're going to have, this is all going to be the same voltage along this part, and then this is going to be the same voltage along this part, so that means that you got VN1 and you got VN2. So then you just want to unfold from there. And if you did MAME, then that's a 4x4 matrix there. So that would be just that would take up a whole ton of time. So it'd just be better to go with it would just be better to go with name. So So let me delete that and let me start on this. So now that we're doing name, you want to get that conductance matrix down. We'll focus on the top left element. And so looking at this, the top left element is going to be, it's all going to be positive, where you see, let's actually convert all these components into conductances. We're going to have 1 over R1. You're going to have SL2 as, no, you have 1 over SL2. Okay, so for the impedance world, you're going to have your resistances are going to be R, your capacitances are going to be 1 over SC, and then your inductances are going to be SL. But then whenever you flip it, 1 over Z, that's going to equal your conductances, which is going to be 1 over R, which is equal to G. You're going to have your capacitances, which is just 1 over SC, which just turns into SC, and then 1 over SL. So then if I go over to here, you have 1 over SL2, since we're going to be doing conductances, and you'll have SC3 for conductances, and 1 over R4. From there, we can start making the matrix, where you have 1 over R1, which is G1. You can follow along here of, oh wait, let me rename this to JG. So you have your current source JG going in at terminal A. If you go along this wire, you'll see the R1 is connected to VN1. You'll see this source is connected to VN1, and then you'll see this inductor is connected to VN1. So all that we have to worry about is 1 over R1 and 1 over SL2, since those are the two passive elements connected to it. 1 over SL2. And then this bottom left is going to be what VN1 and VN2 share. I just realized I wrote this as VN1 whenever that should be VN2, and this should be VN1. Let's rewrite that. VN1, VN2. Cool. So for the bottom left element, we're going to have the inductor being shared between VN1 and VN2. So we're going to make this negative since it's being shared between the two. 1 over SL2. And then top right is also what VN1 and VN2 share. So that will also be the negative SL2. Now we focus on VN2. We see that there's an inductor connected to VN2, a capacitor connected, and a resistor connected. So then we're going to add all of those together as positive values. 1 over SL2 plus SC3 plus G4. Oh, my pad's turning. There we go. VN1, VN2. Then you have your, now we can look at the active sources that are going in. So we have a current source and a dependent source. You have JG going into VN1. So since the top one is the VN1 equation, or since this top half focuses on VN1, JG goes in the top here. And then we see that beta I4 is heading in the direction of VN1. So therefore, it is going to be positive, and it's going to be beta I4 of S. Now focusing on VN2, we see that no sources flow into VN2, so that's just going to be 0. And now we just got to figure out how do we find I4 of S. So we see that I4 of S is flowing across R4. Now current flows from, whenever you see something like this for a dependent source, you see that it's multiplied by something. All that we have to do is we just use Ohm's law. So we have V equals IR, and we know we're wanting I4. So now that we know that we're wanting I4, we see that I4 is running across R4. So it is I4 R4. And then now we have to figure out the voltage. So we have I4 equals V over R4. And voltage can also be taken as the voltage difference. So the voltage of a component is is both of these voltages minus each other. And the way that that works is that current flows from high to low. So whenever it is stating that voltage is running from VN2 to ground, it's stating that VN2 is the higher voltage, so V high minus V low over R4, which equals VN2 minus 0 over R4, which equals VN2 over R4, which, since 1 over R4 is equal to G4, we can say that's G4 VN2. And so now we can plug this into our, or we can separate these sources. So equals, we have our active sources, JG, and then we add, or we split up beta I4 of S, which is beta times VN2. Beta times G4 times VN2. 0. So far, any questions?
No, I'm all good. Thank you.
Okay. Then we're going to split this up into a 2x2 matrix. So it's going to be equal to JG 0 plus, now we see beta times G4 times VN2. Now, since we see that this is already in the top section of the matrix, that means it's going to stay in the top of the 2x2 matrix. So we can make both the bottoms 0 and 0. And since the way that multiplying this out, VN1, VN2, any VN1 items would be in the left-hand column, and any VN2 items would be in the right-hand column. So since we don't see any VN1 component here, we just make the top left component 0, and we leave B times G4 in the top right. And now we're able to subtract both sides. So this turns into G1 plus 1 over SL2, and then 1 over SL2, minus 1 over SL2. We can actually pull out the negative. So because BJ4 when pulled over is going to become negative BJ4, so pulling out the negative, we can pull out the negative for both of these guys. So 1 over SL2 plus BG4. And then the bottom will be 1 over SL2 plus SC3 plus G4. And then that's going to be VN1, VN2 is all equal to JG0. So, sorry for any screaming in the background. I have a lot of nephews. So now
No worries.
VN1, VN1, VN2. So we can pretty much take the we can pretty much raise this to the negative 1 power. I know that there's a certain word for raising a matrix to the negative 1 power to move it over, but pretty much it's going to be this whole matrix raised to the negative 1 times JG 0. But while we're raising it to the negative 1, let's put in values for these. So G1 over here we see is 1 over R1. That is 1 over 0.5 is 2. So it's 2 plus, we see that L2 is 0.25. 1 over 0.25 is 4. So that is 4 over S. Now for the right side, we have 1 over SL2. We know that's 4 over S plus beta times G4. So beta we see as 4, and then G4 is 0.25. So that is 4 over 0.25, so that's the same thing as 4 times 4, which is going to be 16. Now 1 over SL2 is going to be 1 over 0.25, so that is 4 over S. 1 over SL2 again, 4 over S. C3 is 2 times S plus G4, where G4 is 1 over R4, so that will be 4. Negative 1, JG 0. So now we can enter this into the calculator. My calculator, at least, I like to use X as the S, and then I like to use Y as the JG or EG. It just makes things easier. So entering this in. I absolutely recommend a calculator if y'all are able to use one. That makes this so much easier rather than going through Cramer's rule, because Cramer's rule can take a whole ton of time. Especially for the determinant. Like later on, we're going to be taking a determinant of the third problem, and that can take a lot of time just to run through. Plus 4. Raise the negative 1. Open, open. Y. Close, open. 0. Close, close. There we go. So then that is going to turn into, let's see, where's my mouse? Oh, there it is. Vn1, Vn2 is going to be equal to we're going to have 0.5 times S squared plus 2S plus 2 over S squared plus 4S minus 10. And then for the bottom one, times JG. And then for Vn2, I have 1 over S squared plus 4S minus 10 times JG. So now, for this problem, to find the driving point impedance, we are going to have JG times ZDP equals, we see that this is, it's going to equal the change in voltage. So high minus low. So actually, I'm not going to worry about high minus low, but I see that this is 0. This is Vn1. I know this is Vn1 since it's flowing into Vn1. So then it's going to be ZDP just equals Vn1 over JG. So now you're able to get rid of that JG term. and that will give you 0.5 times s squared plus 2s plus 2 over s squared plus 4s minus 10. And so from there, we can use quadratic formula to find out our numerator and denominator. It's good to keep in mind that ZDP, or for Z, it's going to be your short circuit frequencies on top, and then your open circuit frequencies on bottom, or in the denominator. So from there, S is going to equal negative B plus or minus square root of B squared minus 4AC over 2A. And then that's going to equal negative 2 over 2 plus or minus square root over 2, 4 minus 4 times 2, so it's 8. So this is going to equal negative 1 plus or minus square root of 4 minus 4 is negative 4. So square root of negative 4 is just 2 times the imaginary number, and that's 2 over 2 times I. So that equals negative 1 plus or minus, well, I'll use J for this, negative 1 plus or minus 1J. So that's your short circuit frequencies. So now we need to solve for our open circuit frequencies. And that's going to equal negative 4 plus or minus square root of 16 minus 4AC. And so since it's negative 10, that's going to turn into plus 4 times 10. So that's going to be 40 over 2. And that's going to equal negative 2 plus or minus square root of 56 divided by 2. And if I put that in a calculator, negative 2 plus square root of 56 divided by 2, that's going to be 1.74166. Comma, and then whenever you do subtraction, negative 5.74166. So now I'm going to get rid of the right side, so then it's a bit easier, or we got more room here. You start here. Let's get rid of that. Delete this, and delete this. So now with these values, let me open up with a brush. We have our S-plane. We have our imaginary values and our real values. And so poles are represented with X's, while our opens are represented with circles. So our zeros are represented with circles. So zeros are represented with circles, and then our poles are represented with X's. So from looking at this, we have our zeros equals negative 1 plus or minus J. So that's going to be negative 1 is going to be right here. And that is going to be plus or minus 1. Something like that. Now we look at our poles, and we see 1.74. It's going to be right there. And then we have a negative 5.74166. And so from what we can see here is that this section right here, anything in this section means that it is an unstable, or that our transfer function is unstable. Because of that, that means for open circuit stability, open circuit, because open circuit corresponds to the poles and short circuit corresponds to the zeros. So for open circuit is unstable. Short circuit is stable. Let me make sure I got that right. Oh wait, I have that in my emails. I will pull that up just to make sure that I could be confusing the two. I don't think I'm confusing the two. I think it is short over open for impedances, but I don't want to be giving you bad information.
Yeah, I think you're right, because impedance is voltage over current, and voltage tends to short, and current's open.
That's true. Okay.
At least that's how I remember it.
I will pull up the solutions just to make sure.
I did have a quick question though for explaining like whether or not it's short or the stability for open and short. Do you have to like write a bunch, or can you just leave it like that, where it's like open is unstable, short is stable? Because I know for some of the homework, sometimes it's like like you have to write or explain. Like, do you have to explain why it's unstable or stable, or can you just write that it's stable?
So what's going to happen is, if you were to explain that it were stable or unstable, you can either use this graph to explain it.
Yes.
Or you could convert from S domain to time domain.
Okay.
Which that would involve doing partial fractions. And so if you want to do partial fractions and then show how, because it's positive, it has
Definitely not.
yeah, if you have some s minus 3 equals 0 or something, then like e to the negative 3t, something like that, or e to the positive 3t. If you want to go through all that, then be my guest.
No. The graph works well. I wasn't sure if on the test that was all right to write instead of having to go through. Like, I don't know if that made sense. Yeah. Thank you.
No, I get what you mean. I get what you mean. I was just making a joke about it all. But
yeah, for sure.
Definitely try writing the graph, and then from the solutions, something that the main thing was, he says that since one of the poles of the driving point is in the right half of the S plane, then the open circuit natural frequencies will indicate an unbounded response, or the open circuit frequencies are unbounded or unstable.
Yeah, I just wasn't sure if we had to write something like that, or if we could just literally put open unstable.
I think you could put like, let's see. Oh, there's my mouse. Since open circuit, or let's see. You could say since S equals is in the right half plane. It is unbounded. Or I can't say it yet. What was his wording? Response will be unbounded. He says response will be unbounded. And then it does. He also states that, like, since there's no short circuit frequencies in the right hand plane, then the short circuit response, or the short circuit response will be bounded, is what he states. So he states one for open, whether open is bounded or not, and then he states one for if the short circuit frequencies are bounded or not. And then he states that therefore the network driven by a current source will be unstable, but will be stable for a voltage source. But that doesn't look like it's actually part of the answer. It's just like, it seems more of like an explanation of why we would care, is that if the open is unstable, or if open circuit frequencies are unstable, then we want to use a voltage source. But if the short circuit frequencies are unstable, then we would want to use a current source. And I'm not sure the exact logic behind that, but that's not really an answer that's really required. Just make sure that you know if the graph says the poles or zeros are stable or not.
Perfect. Thank you.
No problem. And definitely keep in mind that 1 over z flips it to where, or y equals 1 over z, then flips it to where open circuit frequencies are on top, and then short circuit frequencies are on bottom. And so that would be the answer. Let me see. List these frequencies. These are going to be in radians per second. I think, let me make sure that he states radians per second. Never mind. He does not state that these are in radians per second. So if you have S equals something, you don't have to write it as radians per second. But if you write omega 0 or something, or if you're finding the omega values, then you do have to use radians per second. So S is unitless. Do you have any questions before I move on to question 2?
I'm all good. Thank you again.
Awesome. Question 2. So for question 2, we need to derive a voltage ratio transfer function. And we see that there's V4. So that's probably going to have some combination of this. So we'll find out whenever we get there. And then once we find our transfer function, we want to find the scale constant, K, and the poles and zeros of GV of S. So it's kind of similar to what we just did, except we don't have to worry about if it's like bounded or unbounded, and we don't have to attach a source since EG is already attached to the whole thing. So looking at this, if we did name, then that would be 1, 2, 3 different voltages in order to account for all components, and so we probably don't want to do that. And then if we do MAME, we see that it's just 2 loops, so MAME is preferable. So for MAME, we know MAME is Z matrix, I matrix equals V matrix. V equals IR. So then whenever we're forming the Z matrix, let me declare my I1 and I2. I1, I2. So we go around this whole loop and we see L1. Let me convert everything to S domain. So SL1, R2, R3, 1 over SC4. So for MAME, we look at our first loop, and we go around, we see EG, we see SL1. So SL1 is going to be the first one we put up here in our top left corner. We keep going around, we see R2, and we'll just add that in. We see a dependent source, but we're not worried about sources right now, so we'll move on to what does I1 and I2 share. And so we see the R2, I1 comes this way, I2 comes this way, and therefore they share R2. So negative R2. And then negative R2 here as well, since it shares. And then this one is for all the passive elements going around I2. So we see R2 is in here. And then we keep going, R3 is here. And last component is 1 over SC4. And then we draw our currents, I1, I2, and then we worry about our voltages. So looking at I1, we see that positive says that its voltage is flowing this way, and I1 flows the same direction. So therefore, EG is positive. And then flowing again, we see that the positive points in this direction for the dependent source, and our current happens to point in the same direction, so therefore it's positive. So we'll do plus mu times V1 plus V4. And then looking at I2, we see that its current runs against the positive direction that the dependent source is pointing at. So it's going to be negative mu V1 plus V4. So then we split these. We got EG, we got 0. Now we got our dependent sources in their own matrix. Mu times V1 plus V4. And then we have negative mu times V1 plus V4. Now we gotta figure out what V1 and V4 are. So looking at V1, we see there it is right there. So I1 runs across it. It's going to be, we're going to use Ohm's law to figure this out. So we know V1 equals our current running across it, so that's going to be I1. And then it's going to be multiplied by its impedance, which is going to be SL1. And then we look at V4. Well, V4 is, again, our current running across it, which is going to be I2. And then we're going to multiply it by its impedance, which is 1 over SC4. So now that we got that, we just plug it in. It's going to equal EG 0 plus mu times, let's see, V1 is SL1 I1 plus V4 is 1 over SC4 I2. And then we just make it negative for this bottom one, SL1 I1 plus 1 over SC4 I2. Cool. Now we gotta split it up into a 2 by 2 so we can correctly fit it back into the original matrix. EG 0. So for this, we see for something like this, let me close this. It's going to be I1, I2 for this second part. Therefore, this is our I1 column. This is our I2 column. So for I1, we see that we have one component for I1 here, and that's going to be our mu SL1, which I'm going to move everything to, I'm going to move the S to the right. UL1S, and then we have our mu 1 over SC4 I2, so that's going to be mu 1 over SC4. Now at the bottom, it's just going to be negative for all those components, UL1, S, and then mu, negative mu 1 over SC4. Now we gotta move it to the left. So this is gonna look like, I'm just gonna move this up here. That's gonna be SL1, well, let's see. So we got UL1 and SL1. So we can pull the S out of that. Or we can actually pull out the SL, the S and the L. So we can do SL1 times, we have a 1 here, and then we have a negative mu here. So it's 1 minus mu. And then let's go to the bottom one here. That's going to be negative R2 plus mu L1S it doesn't seem there's anything we can combine. So, I mean, we can pull out the negative. So negative R2 plus mu L1. Now we can go to the top right one here. We have negative R2, and since the mu is positive on the right side, it's going to turn negative. So we can pull out both the negatives. So it's going to be negative R2 plus mu over SC4. And then the bottom right one is R2 plus R3. And then since it's negative in the right side, we're going to pull over the mu and make it positive. That's going to be plus 1 over SC4 times 1 plus mu. Then close that off. We got I1, I2, and that equals EG 0. Now we just move it over to the right side. Or we're going to, let's plug in the numbers first, so then it makes the math a little bit easier. So SL1 times 1 minus U, L1 is going to be 1, so that's just S times 1 minus mu, and mu is 2, so S times 1 minus 2, that turns into negative S. And then on the right side here, we have negative R2 plus mu over SC4. R2 is 5, so that's going to be negative 5 minus mu is going to be 2. 2 over 1, so that's going to be 2 over S. Negative R2, that turns into negative 5 minus mu L. Should this have been... Oh, I knew that I was forgetting something. Mu L1S. Is there an S in here? Yes. Okay, cool. So now everything's right. I forgot the S right here, but I added it in. Negative 5 minus mu L, so that's 2 times 1, so that's negative 5 minus 2S. And then the right side is going to be R2, which is 5. R3 is 1. That's going to be 6. Plus 1 over S times 1 plus mu, so that is going to be 3 over S. I1, I2. And then we got EG here, and we got a 0. And now we move that over. I1, I2. Then the right side is going to equal. Let me pull it up on my calculator. It's going to be negative x, comma, negative 5 minus 2 over x, close open bracket. Negative 5 minus 2x, comma, 6 plus 3 divided by x, close, close, raise the negative 1, open, open. Then we got EG, and I'll replace that with Y, close, open, 0, close, close. And that gives us some pretty big numbers. Let me look just to make sure this matrix is right. Negative S, negative 5 minus 2 over x. Yes, negative 5 minus 2. Okay, I think this is right. Yeah. So then what this is going to be, one second, let me just check the solution. I feel like I missed a number. Yeah, I think I did miss a number. Let's see. I dropped the R2. I dropped the R2 in the top left corner. Plus R2. So then that's negative S plus 5 So this should be 5 minus S. Did I miss anything else? Negative R2. Okay, I got everything else. Yeah, I was missing R2, and I felt like the gain on what came out was wrong. 5 minus. Nope, it still came wrong. 1 second, let me go through each of these numbers.
No problem. We've all been there.
Let's see. So R2 is 5. Let's see. So this is supposed to be, the final matrix is supposed to be R2 plus SL1 times 1 minus U, or mu, which looks like what I have. And then the right side is supposed to be negative R2 plus mu over SC4 negative R2 plus, okay, it was supposed to be negative R2 minus mu L1S. Let me see. So whenever this comes over, you have negative 1 or negative mu L1 of S, or S. You move it over and it becomes positive. So it's negative R2 plus mu L1 of S, which, since I wrote negative of both, that would be wrong. This one right here is actually supposed to be negative. So that means this should be positive 2S. Therefore, and let me just keep running through this so I didn't make any other mistakes. Negative mu L1S. And the right one is supposed to be R2 plus R3 plus 1 over SC4 times 1 plus mu. Okay, that looks like that was the only 7 billion mistakes I made, but I think we should be good now. Let me enter that in. 5 minus x, negative 5 minus 2 over x, negative 5 plus 2x. There we go. That looks much better. Okay. So this then equals 1.5 times s plus 0.5 times EG over s squared plus 1.5 s plus 1.25. Then this bottom one is negative 1 over 2 times s times s minus 2.5 times EG over s squared plus 1.5s plus 1.25. So now with that, we can see that the gain, or the scale constant k, is negative 1 over 2. So we can say k equals, or wait, so before I start saying that, I need to go back over here to GV of S equals V4 of S. So we have GV of S, let me write the G better, GV of S equals V4 over EG times, since we're bringing this, or wait, sorry, not times, V4 over EG. V4 we know is I2 times S1 over SC4, so that just naturally comes down to I2 times 1 over SC4, and we get rid of the EG, which that equals, are -1 over 2. And since C4 equals 1, it's really just trying to get rid of that random s we see here in the numerator. 1 over s times the s times s minus 2.5 over s squared plus 1.5 s plus 1.25. So far, so good. We're able to cancel that s, cancel that s. We now see our k is equal to -1 over 2. And since it's a scale constant, it has no units. It's unitless, so we don't have to worry about that. And then for poles and zeros, that is going to be s equals 2.5. And then for this next one is going to be, we're going to break, let me do this for poles. I like to do zeros, and then s equals 2.5. And then for poles, s equals -b plus or minus square root b squared minus 4ac over 2a. And then that equals -1.5 divided by 2 plus or minus square root of 1.5 times 1.5 squared is 2.25 minus 4 times 1.25, which would be 5 over 2. And then this equals -0.75 plus or minus, let's see, square root of 2.25 minus 5 divided by 2. It's going to be 0.829. 0.829156. And this is our pulse, and then this is our 0. So now that we have that problem done, is there any questions you have or concerns?
No, I understand that pretty well. Thank you.
Awesome. And we'll go over to problem 3. Actually, let me clear that is the solution. So for this problem, I don't know if it's going to make you lose points or not. So it says poles and zeros of GV of S. And so whenever it says GV of S, that means you just assume that it's going to be a function of S. And so you're not going to like substitute it. For some reason in his solutions, he at the end, even though the S equals J omega, he does say the 2.5 is radians per second. And then this is also radians per second. So I think if you are unsure of if like you come down to S equals something and you're not sure if you're supposed to write something for that problem, I don't think it'll hurt you if you write radians per second. Because it's pretty much like imaginary radians per second, because you just have J times 2.5, I guess. I mean, no, it's not J times 2.5, but it is, yeah, I don't think it'll hurt you. But like if it asks specifically for frequency, or if it asks you specifically for angular frequency, then definitely write radians per second. If it asks you for poles and zeros, his solutions have radians per second, so if he tries to take away points, you can argue with him, like say, hey, your answers have it wrong. Or have your answers say otherwise.
Sounds good, thank you.
Awesome. So test question 3. So for test question 3, we're wanting to find frequency of oscillation, which, as I was mentioning earlier, oscillation is finding at what point does the do the values like fall along the imaginary axis, or like pretty much IM of your denominator d of s equals 0. That's pretty much what you're trying to find whenever you're wanting the frequency of oscillation. But then, of course, since we've always been dealing with MAME and name, how does this necessarily affect us is the first, like, how is this going to affect the process of how we usually do this? And it doesn't affect it too bad. We're still going to be using, we're always going to ask ourselves the question of, do I use MAME or do I use name? And so looking at this, we can tell this is a pretty easy MAME question of a 5x5 matrix. So just solve the 5x5 and you'll be good. But if you don't actually want to do a 5x5 matrix, we can always just do the 2x2 name. So with that, we have VN1 and we have VN2. So with VN1, we're going to look at all the passive elements going into it. We see a dependent source, so we save that for later. We see G1, C2, L3, those three components enter into VN1. So it looks like everything's, the resistors have been converted to conductances, which is awesome. And our capacitors, they're usually 1 over SC2 for impedance, but for conductances, that's 1 over SC2. So therefore, that's going to be SC2. And that's going to be 1 over SL3. And then we're going to have SC2. Did this like get bigger? I feel like the size got bigger. Let me see if like, oh, there we go. Let me see if I can adjust. I feel like the size got, was this? No, it was definitely, it wasn't changed. Never mind. I'm just imagining things. Okay, so then with this, we see our three components going into VN1. So that's just going to be G1 plus SC2 plus 1 over SL3. So with that, now we're going to do our what's shared between VN1 and VN2, and we see it's that inductor, so that's going to be negative 1 over SL3. From there, we can see, oh yeah, also, and the top right is also going to be what's shared between the two, so negative 1 over SL3, and the bottom right is going to be what passive element's going to VN2. You see there's an inductor, capacitor, resistor. So for that, it's going to be 1 over SL3 plus SC5 plus G4. Then we, since this is name, this is going to be our conductances, this is going to be our voltages, and this is going to be our currents. So our voltages are VN1, VN2, and that's going to be equal to our dependent sources, which we see that this one flows directly into VN1, so that means if something flows into it, that's going to be positive, and if it's trying to flow away from it, that's going to be negative. So we see BI5 of T is flowing into VN1 of T. So then that is going to be BI5 of T. And then this is going to be negative GM V2 of T. So now we want to separate these, or we want to figure out what is I5 and what is V2. So we see that I5 is the capacitor here, and we can use Ohm's law to figure this out. So we have V equals I5 of whatever the impedance is of the capacitor. We know that V is change in voltage. So it's going to be change in V equals I5 times its impedance, which is going to be 1 over SC5 for a capacitor. And then we just move this over to the left side. That's going to be I5 equals SC5 times the change in voltage. And so, I think, that is going to be Vn2 because the current is flowing into it. Since the current flows into it, therefore Vn it's going to be positive, and it's flowing into Vn2, so it'll be positive. Now that we know that this is going to be positive, now we look over at SC2, and a good way to think of this is this component is going to be negative, and it tripped me up the first time that I looked at it, but the best way that I recommend, let me check the page again just to make sure, because this is my biggest pet peeve in circuits, is that some of these for some reason feel like they randomly flip between negative and not negative. Gosh darn it, I knew it. Okay, so I5 is actually wrong here. It is negative.
It is negative since it is going from positive down to negative.
Yeah, and I was trying to say not like high minus low, and then it's going to be negative Vn2, and so
it is negative?
It is negative. So that let me rewrite this then.
That's so confusing sometimes.
I know, it annoys me so much in circuits. That this is like the biggest thing that always got me.
Because you assume a positive orientation. Whatever.
Yeah. So you're going to have the conductance G, or let me say conductance as an SC5, and then you're going to have the high voltage, or current flows from high to low, V low, and so since it's flowing up, that means this is high and this is low, and that means that I5 is going to equal SC5 times 0 minus Vn2. And so that is why I5 is equal to SC5, or is equal to negative SC5 Vn2. Now in terms of V2 of T, to find that one out, it is going to be the positive voltage minus the negative voltage. So this is also going to be negative, where this is going to be 0 minus Vn1 equals V2 of T. Or let me write this as a better way of explaining it. You want the change in voltage across capacitor 2, and the change in voltage is going to be the difference between these 2 points. Now, the positive, or the high voltage, is going to be the positive area is going to be the 0, because the positive faces the 0, and then the negative side is going to be the Vn1, since the Vn1 is what the negative side faces. Or this 0, or positive faces 0, negative faces Vn1, therefore Vc2 is equal to 0 minus Vn1, which is going to be negative Vn1. And I feel like this is probably how he fixes the curve of everyone, is that he throws in questions like this. So now that we know that they're both negative, this is going to equal beta times I5, which is going to be negative SC5 VN1. And then the bottom one is going to be negative GM V2 of t is going to be equal to our VC2, which is negative VN1. So that's going to make this positive VN1. Now we're going to split it up into a 2 by 2, so we're able to subtract it from both sides. And that is going to equal, let's see, so we have a VN1. So VN1 is this column. Oh, that's a mistake. VN1 is that column. VN2 is this column. So VN1 goes here, negative beta SC5, and then GM for right here. That's going to be 0, 0, since we have no VN2 terms in either the top or the bottom. VN1, VN2. And now we're going to subtract it from both sides. So now, looking at this new matrix, we have G1 plus SC2 plus 1 over SL3 plus beta SC5, and then negative 1 over SC3, or is it SL3? SL3, that's what it is. SL3, negative 1 over SL3 minus GM. And then, since the rest are 0, these are all the same. Negative SL3, 1 over SL3 plus SC5 plus G4. VN1, VN2 equals 0, 0. So, the way that this next part is going to work is that whenever we do Cramer's rule, if we were to do Cramer's rule on this or something, or if you were trying to enter this into a calculator and solve for VN1, VN2, you're going to get 0 for both because there's no active sources providing any power to the system. So what we're going to do is, we know in Cramer's rule, we're focusing on determinants. And so the important thing is that whenever we do these determinants, the determinant of V1 or VN1, or we're going to solve for dVN1, we're going to solve for dVN2, and then we're going to find the determinant. And then it's going to be VN1 equals dV1 over d, and VN2, let me write that. VN2 is going to equal dV2 over d. Well, what that means is that since there's nothing in the numerator, the determinant is going to be the only thing that matters here. So we're just going to take the determinant of this whole matrix right here. Because, I mean, if you were to find dVN1, this part would become 0, this would become 0, and then crossing that becomes 0. And then if you were to do dVN2, that becomes 0, that becomes 0. You find the determinant, and then the determinant of that is 0. So dVN1 and dVN2 would already be 0. So really the only numbers that you could really get any information out of is the determinant right here. So for that, the best way to go about it is to plug in numbers already. Just like go ahead and plug in values for G1 and C2 and L3. Later on in exam 2, that might not be possible. I'm trying to remember. I used to do it on a computer where I would leave it as variables, and I think you had to find you had to find it in like a variable form of like you couldn't put in numbers until the very end. And I think that was for exam 2. And I had to use a computer for that because the math was way more than 1 page and we only had 50 minutes to do the exam. But it worked. But I don't know if he allows computers anymore.
So do you think for exam 1 you can just leave it in numerical form instead of symbolic?
Yes. For exam 1, I absolutely recommend going numerical.
Okay, that sounds good.
So we're going to plug in 2 here, 2 plus SC2, that's going to be plus 2S, 1 over SL3, L3 is 0.5, so that's going to be 2 over S, plus BC5, so beta is going to be 19, 19 times C5, C5 is 1, so that's going to be 19S. 1 over SL3, that is going to be 2 over S. GM is going to be... Oh, right, we're going to be solving for GM later. So GM is going to be left there. Negative 1 over... If your calculator can do determinants, I would highly recommend finding out, because that would probably be a really good thing for this part, is just to be able to plug it in and then just replace the value of S, I guess, with a variable X or something, and then replace GM with the variable Y, and then that'll just come down to a bunch of X's, and then you can just replace the X's with J omegas, and then we'll show you in a bit what to do from there. So you got negative 1 over SL3. That becomes negative 2 over S. Now we have 2 over S here too. SC5, that's going to be just S. G4 is going to be 3. So we got VN1, VN2. Oh, sorry. Oh, wait, no. Yeah, that's right. Equals 0, 0. So now with that, I'm actually going to add this stuff together. Actually, just for this, I'm just going to delete that. It's going to be 19 plus 2, so that's going to be 21. So I'm just going to write 21S there. There we go. And so now we're going to do the multiplication. 2. And this is going to turn into plus 2 over S. Am I sure this is right? V2 of T is this one right here. V2 of T is related to VN1, so that goes in the VN1 slot. I5, wait, that's VN2. Wait. I knew there was something fishy about this.
I'm sorry, I didn't even notice that.
It's all good, honestly. It's it just takes one mistake.
That's the bad part.
I know, it just
I've literally been looking and I just haven't noticed it.
I was like, I did this earlier, and I was like, wait, where'd the 21 come from? Because I didn't remember having to work with a 21. I remember having to work with a 19. Well, we're going to select this, and we're going to get rid of this monstrosity. And we're going to fix that guy. And then I guess I'll move this guy over here. And then I will move this guy over here. It's as if nothing ever happened. Plus BS5. Yes.
Practice makes perfect.
Exactly. I would never change this, Dr. Russell, I swear. Let's see. So that's going to be plus 2S. Or C2. Yeah, C2 is 2. So plus 2S. And then we have 1 over SL3 plus SC5, 2 over S plus 3. And then this is going to be Let me do that. Let's select this, because now this is going to become negative. This part right here. Okay, so this is going to be negative. This part right here is going to become negative 1 over SL3 is going to be 2 over S, negative 2 over S. Beta is 19. C5 is 1, so it's going to be plus 19S. So then we have negative. I'm going to start from here since this has the negative sign. So I'm going to pull the negative sign down. So we're going to have negative 2 over S minus GM, and that's going to be multiplied by negative 2 over S plus 19S. And then this negative sign is going to cancel out. But I will do that after I do the multiplication. 2 times 2 over S, that's just going to be 4 over S. 2 times S is 2S plus 6 after we finish multiplying that. We got the 2S times 2 over S, and the S's are going to cancel out, so you got 4. We got 2S times S is going to be 2S squared. 2S times 3 is going to be 6. And then we got 2 over S times 2 over S is going to be 4 over S squared. Then the S's are going to cancel.
Wouldn't 2S times 3 be 6 over S for that?
This one?
The 2S squared, yeah. Would that be 2 over S?
Let's see.
Or 6 over S, sorry.
2S. Oh, wait, so I had the 2S squared, so 2S times S. 2S squared. 2S times S. Yes, you're right. 6S. It becomes 6S. Because 2S times 3, 6S.
Okay.
Thank you for catching that.
No, you're good. I was trying to, because I was listening, and I was like, wait, hold on, that didn't make sense.
Hold up. This man is crazy. Let's see. 4S.
No worries, I was just trying to help. I didn't want to.
Absolutely. Thank you very much. Because that saved me like 5 minutes of reworking this whole thing. 2 over S times S is just 2. 2 over S times 3 is just 6 over S, like you were saying. 6 over S. And now we got this negative sign. I'm going to turn this positive and just take out the negative sign here. So then this is going to be plus 2 over S times negative 2 over S is going to turn into negative 4 over S squared. So something's going to cancel out in a second. 2 over S times 19S is going to be 38. Yeah, just 38. GM, that's going to be negative 2 GM over S. Then 19 GM. 19 GMS. Cool. And so now that we got all this, now we got to simplify this whole darn thing. And you can already see, like, this problem is taking, like, 23 minutes, maybe. I don't know. Like, maybe it'll be less whenever you're just thinking in your head, but, like, already, like, the math is just so much for a determinant. Let's see. So, let's start with 4 over S. Is there any over S's? We have a 6 over S. So let's say 10 over S. Any other over S's? Nope. Oh, wait. Yes, there is. Minus 2 GM over S. So now we have the 2S here. Which, any other S's? Okay, so we got 2 plus 6. Awesome. 8S. Now we got 6. That's 6 plus 4. That's 10.
12. 50.
38. Yep, so it's going to be 50. Let's see. So we got through no S's, so now we got 2S squared.
That's the only one, I think.
Awesome. And then we got S, that was accounted for. 4 over s squared. Those cancel out, and there's no other 4 over s's squared. I think those are all the numbers. So now that we have it here, you'll notice.
Oh, I think the plus 19 GMS.
Oh, wait. Yes, you're right. You're
good.
So I'm plus 19 GMS. Am I missing anything over here? No. Okay, cool.
Yeah.
So from there, you'll notice that there's an over S piece. And what you can do is you can factor this out. You can do 1 over S times 10 minus 2 GM plus, let's do 50 here. So it's going to be 50S. It's just raising everything in S, or it's multiplying everything by an S. So 50 times S plus 8 plus 19 GM S squared plus 2S cubed. And this won't affect anything, or this is the proper way to go about the answer, because if you went with this one, then it would have gone weird. But the reason why this works is that if you have some kind of transfer function where you got a numerator of s, and you got a denominator of s, and you pull out an 1 over s, then really that's just s times n of s over d of s, and now it's not really part of the denominator. It's whenever you see a 1 over s, that's really part of the numerator, or it affects the numerator, not the denominator. And that's why it's important to factor out any of those over s's to get just 10 minus 2 GM plus 50s plus something s squared plus something s cubed, etc. And so if you see something that's just 1 over s squared, you pull out 1 over s squared, and you just really multiply everything by s squared.
That makes sense. Thank you.
No problem. So from there, now we have our, this is equal to, we have our d of s. And so like if we scribble out the 1 over s, this really just leaves us with the remaining parts of d of s. Now, there are 2 equations that are going to form from this. Once you have your determinant d of s, where's my mouse? There it is. Once you have your d of s, you're going to form 2 equations. Let me get rid of these voltage calculations stuff. Delete. There we go. So once you have your d of s, you're going to form 2 equations, and one might solve to help the other, or the other one might help solve in order to be able to do the other. Pretty much the first thing is you're going to find your frequency of oscillation, and then you're just going to plug it in to find your GM, or plug into the other equation to find your GM. Because what you can see here is if I start with the imaginary, actually, let's start with the real. If I start with the real parts of d of s, what we're going to get is, so 50s, that's going to turn into j omega. And so since it has a j, that means it's going to turn imaginary. So if it's an odd number s, if it's going to be s or s cubed or s to the 5th or s to the 7th, then those are imaginary parts, because though s to the 5th is going to turn into j omega to the 5th, and that's going to be equal to -1 times -1 times j omega to the 5th. And so since there's a j in there, that makes it imaginary. So that's why if you see s s cubed, s5, s to the 5th, or s to the 7th. Those are imaginary parts. While if you see a real number plus s squared plus s to the 4th plus s to the 6th, any of that, then those are going to be the real parts. So looking at the real part, we see 10 minus 2 GM. So is that going to be the real part or the imaginary part?
Real.
Cool. So then we'll add that into it. 10 minus 2 GM. Now we have 50s. Is that going to be real or imaginary?
Imaginary.
Yep. And so then s squared, what's that going to be?
Real.
Yep. So then we're going to add
minus 8. Or
8. Wait, is it going to be minus?
Or if it's j squared, it'd be minus 1, right?
Oh, true. 8
I'm
plus.
not sure if that's right.
I think it's just going to be like plus 8 plus. Oh, wait, yes. What you are saying is right. It is going to turn negative because of s squared. I'm just going to do the multiplication just in a second here.
Yeah,
s squared. And then we have no s to the 4th. So we're
and
good.
then don't forget the GM attached to 19, by the way.
Yeah, I'm already dropping things.
No, you're fine.
See, I'd already fail circuits too if I took it.
No, I'm trying to help.
Thank you. Equals 0. So then we got 10 minus 2. That looks like a 20. 10 minus 2 GM. That's going to be minus 8 plus minus 19 GM. Actually, wait, what's the best way to format this? This is going to turn into, maybe I should write it all out. Plus 8 plus 19 GM times j omega squared. Or j squared omega squared equals 0. And that's going to turn into 10 minus 2 GM minus 8 plus 19 GM omega squared equals 0. And then from there, you can see that the we have two unknowns. We have GM and we have omega squared that we really can't solve for. So then it's like, okay, so now we need to switch to the imaginary equation to really figure out what is going to be our value. And so for that, I'm going to get rid of some of the name work so that then we can actually get more space for the imaginary part. So we'll just work on the imaginary part up here. I am of, oh, that was a horrible bracket, of d of s equals 0. This is going to be the 50s, 50 j omega, plus the 2s cubed, so 2 times j omega cubed equals 0. And that's going to turn into 50 j omega minus 2j omega cubed equals 0. And then you can pretty much take out the j. You can divide both sides by j. And then that's 50 omega minus 2 omega 3 equals 0. Then move the 2 omega 3 to the other side. And then you got 50 equals 2 omega, 50 omega equals 2 omega 3. And then you can divide both sides by omega. And that'll get you 50 equals 2 omega squared. And then that gets you omega squared equals 25. And then omega equals square root of 25, which equals 5. And then from there, F0 is going to equal, 2 pi F. Let's do this. It's going to be omega 0 pretty much. 2 pi F equals omega 0. So you just move it over F omega 0 over 2 pi equals 5 over 2 pi. And then that equals, let's see, 5 divided by 2 divided by pi is equal to 0.795. Hertz.
This might be a dumb question here, but is there such a thing as negative frequency? So when you take that square root, you would take the negative part of it, or you always take the positive, I assume?
Technically, there are negative frequencies,
okay,
but just not in the real world.
Okay, so just take positive.
Yeah. Because what you'll see is if you were to do if you do a frequency transform of cosine 3t, then I mean you'll find this later in like continuous systems and such, but this is going to equal 1 over 2 times e to the 3j minus e to the negative 3j. Okay. Anyway, there will be like two components that will kind of appear, and then if you were to graph that on a frequency, if you were to graph a cosine wave, then there's going to be a negative frequency component and a positive frequency component. And the way that that kind of shows itself is that if you are doing some kind of like AM modulation or something where you have a signal that has a very small frequency, then you go, and that's in like maybe 400 hertz. You got a 400 hertz signal, and then you attach it to a carrier wave that's like, let's say 20 kilohertz. Then essentially you have a frequency that's like 2 kilohertz plus the 400 over 2, and then it's pretty much like that's how much bandwidth your signal covers. And so there is such thing as negative. It's just whenever you boost up to a lot higher frequencies, or enough where that frequency is shown, you can like, it's a bunch of bandwidth stuff, pretty much.
But fine, I got you.
Yeah, no problem. And let me see. So we got our frequency of oscillation. And so then from there, now we can plug in our omega 0 value, square root of 25, and the square root cancels out with the omega 2, or omega squared. So it's 10 minus 2 gm minus 8 plus 19 gm. Omega squared turns into 25 equals 0. And then it's going to be 10 minus, let's see, 25 times 8 is going to equal 200. So it's going to be 10 minus 200 minus 2 gm minus 19 times 25. That's going to be 475. So it's going to be 475 gm equals 0, which means that gm is essentially going to be negative 190 over 477. Negative 190 by 477. All right. Negative 190. Yeah, because then it's going to be negative. Wait. I will make sure this is right. 1 second. 10 minus 2 gm minus 8 minus 19. 10 minus 200. Yeah, there's going to be 3 negative components, and then the 10 is the only thing that's positive. So 10 minus 200 turns into negative 190. And then gm is also going to be negative, so this is negative 190 minus 477 gm. Both sides, I remove it to the other side. It gets you gm equals 477 equals negative 190. And then that's gm equals negative 190 over 477. And that equals negative 0.398. 323. And then that is your GM, and then that is your frequency of oscillation in hertz.
Perfect. That made sense. Thank you.
Awesome. Well, if you have any other questions, then you can ask me, or if any pop up later, then you can also ask me then.
Yeah. I appreciate it. Thank you for holding the session.
No problem.
Yep. We'll have a great rest of your night.
You too.